In the previous two videos, we set the stage, and in this video, we'll do a code review of APB Blinky, which is Blinky with an APB interface. And so, again, Verilog module starts with the keyword module and the name and the parameters. In this case, there's no parameters, so I just put that there as a placeholder so you can see an example of what a parameter would look like. That part could be easily deleted if we wanted to. So it starts with module all the way at the bottom, end module, terminates the module. Then you have a port list with all your inputs and outputs, the clock. So we have the clock at the reset like we described in the previous video. And the new signals are the APB interface, which is an address, it's a 31-bit address. Potentially it might be less, but in this case I made 31 bits, 32 bits. That's like 31 down to 0, 32 bits. Then we have a Boolean, a 1-bit um, select signal. So, and we have a p-enable input. We have a p-write input. We have a write data bus, which is 32 bits. A read data bus, which goes back to the processor. And that's another 32 bits going the other direction, two separate buses. And then we have a p-ready signal, which we'll talk about. It's always driven high. And then we have back to our regular old Blinky, the LED, which blinks at some rate that gets defined by what the processor writes into it. We have a few internal state registers. You can view these as private variables if you like. One of them is the blink rate, which is how many clock cycles is it high, how many clock cycles is it low. And so that's what we call the blink rate. And then we got the PR data bus, which is just the data that gets returned to the processor. And the P-ready signal, which again, I told you is always going to be high. Now we get into this always block, and we discussed it in the previous one, but we'll hit it again. In that an always block, it's like a method, but it triggers every time there's a rising edge, pause edge. At the pause, you can read it as at the positive edge, the rising edge of clock, do everything in here, and then stop and wait for the next rising edge of the clock. So it runs this entire code, and it stops, waits again, gets another one, and it runs it again. So at the beginning, you might have reset end low, which resets the block. All these guys get set to the initial values. In this case, I made blink equal to 128 so that it'll kind of blink even if it's like coming out of reset. So the process doesn't do anything, but you can still see the light blinking. Figured that'd be a nice touch. You could just as easily make it 0. No, it doesn't. It's your choice. Um, and then if it's not reset, so not at the right at the beginning of the test, um, that's the else block. And then we go in and we take a look to see if P cell is high and P write is high and P enable is high. Then we have this case statement where we look at the address. In this case, we're just looking at the lower 8 bits of the 8 address. The address is 32 bits. We're only looking at the lower 8. You can look at full of them and just all 32 just makes it a bigger decode. And then if the lower 8 bits was equal to 4, then we take whatever's on the right data bus and we put it into the internal register of of blink rate. If it's any other value, then it falls down to the default, does nothing. And so this happens every clock cycle. So every 10 nanoseconds, if it's a 100 megahertz clock, falls down through, checks and reset, not reset. It checks these signals here and checks the address and assigns it if it's there. If nothing is happening, every clock cycle it does this one task over and over again. That's what this always block does. So you can see it if we're in here. Now we got the P cell going high. Oops, that's the first condition here. And then P right is high. Where's that? Oh, we got a P right high and during this time. Oh, we got a P right. And then, ooh, right here, P enable is not high here, but it's high here. So right here on this clock cycle, you got this guy high, this guy high, this guy high. So you fall into this into this if condition. Check out the P address. P address is here. The lower 8 bits is 04. And so that's a 04 compat matches the 4. Boom, you win. Whatever's on the right data bus, which is in this case is hex 12B, that gets written into the blink rate, and then that gets assigned. In the next clock cycle, we got all these signals are low, so this guy is low, so we don't fall into it. We don't fall into it again until we get over to here when we have P cell high. Ooh, that's good. P right. Ooh, that's low. That doesn't happen. Now P enabled with 2 out of 3, but you need all 3. So basically, this is the only write that's happening in this simulation. And you can see it just keeps repeating this every clock cycle, looking to see, oh, should I update this guy? Should I up this game? Should I? It just keeps going on and on and on. So that's the write operation. Similarly, what I've done here is it's a pretty dumb thing, is that I only have one value that gets read. I guess I could put a case statement to make it more expandable. I think we will do that. Why not? Um, let's take this guy here. Control C. Control C. Control V. Oh dear. All right. Pick him out of there. Put him in there. And then we'll put another value for when it's anything other than 4. Let's drive the data bus to 0. Why not? All right. So in this case, so that's kind of something that can scale. Hopefully it still works. So we've got an address. So in this case, we're not even looking at any of these enables and write signals or whatever. I'm just going to drive onto the address, the read data bus, whatever the address is selecting. So if it's a 4, it puts out a blink rate. If it's something else, it puts out 0. And so let's see if that still simulates. That's interesting. When I touch stuff, it tends to break. Control Z, BG, enter, up arrow, up arrow, enter. Cat, /C, tab, enter. Oh, great. That's a good start. /RU, tab, enter. Ooh, it still runs. That's great. Yeah. Um, so basically, I'm always just put out the write bus. Processor can do what it wants to when we're not getting accessed. So I've chosen to just drive the read bus whenever the address is there. Ignore all the other control signals. It's a perfectly valid thing to do in FPGA. There's nothing wrong with that. Um, and then we got the ready signal. And then what we've got is, so whenever we do write into it, we update the blink rate here, boom, because we finally got, how do we get it up there? So we finally had a write. We write this guy, we write it to 12B. Where'd the code go? So we update this blink rate, and then this blink rate, if we fall down into our other, essentially code that we had from previously, if the count is less than, like this used to be a constant, and if the count is less than blink rate, we increment the count. Else the count gets cleared back to 0. So this counter is going to count from 0 up to blink rate and then go back to 0 again. 0 up to blink rate, back to 0 again. Pretty boring life, but that's all it needs to do. And then if the count equals 1, I pick 1 because always if it's reset to 0, then it'd always be toggling. But so if the count is 1, then the LED is going to be toggle from 0 to a 1. So if it's a 0, it becomes a 1. If it's a 1, it becomes a 0. Um, and so, yeah, that's how we can implement this Blinky guy. And just to make sure it still does do a Blinky, let's see, we should have a GPIO LED. Control W, no, Control W doesn't work. Drag it over. And, whoa. Let's zoom out. Oh yeah, there it goes. So it is toggling nicely. And so I believe, what else? Anything else we want to talk about in this code before we move on? Yeah, that's it. We'll hit the test bench in the next video.